Hey everybody, welcome back to another video. So in this video, we're going to talk about hemoglobin structure. We're going to touch on, in very big detail, on oxygen and CO2 transport, just linking everything we've been talking about in the past 3 or 4 videos together. So I really want to emphasize, if you haven't watched those videos, you're going to have a harder time understanding what's going to happen here. So I would recommend going back, watching those videos in this playlist, and coming back to this video. Okay, and as always, if you guys like the video, if you get something out of it, please consider subscribing and liking the video. And if you have any questions, comment down below, and I'll answer it. Okay, let's get started. So before we start talking about any of our other discussions, the key thing here is talking about hemoglobin. Okay, hemoglobin is the structure that makes all of this possible. Okay, all this transport mechanism. Now, there are multiple things that can happen with hemoglobin, as in it can change its shape, it can bind to multiple things, and so it requires a little bit of understanding. Okay, so firstly, here is my depiction of hemoglobin. Okay, you guys know that hemoglobin has 2 parts in the name, right? So hemoglobin, okay? There is a heme portion and a globin portion. But what are they and where are they on this specific drawing? So in blue, okay, circle here is a heme group. And if you guys know, heme group in this scenario has an iron in it, okay? Heme groups have iron. So they contain an iron, specifically in the 2+ state, okay? So this is a ferrous iron. This iron is what's actually binding the oxygen, okay? And then after binding the oxygen, it'll oxidize the iron into a 3+ state, okay? But that's neither here nor there. Really though, all I want you to know is that in this drawing, this blue dot is the iron-containing heme group, okay? And the iron is in this 2+ state. Once oxygen binds, it turns into a 3+ state, okay? Because it oxidizes it, okay? Now, what else? So that's where the heme is. What about the globin? What about the globin? Well, you guys know that hemoglobin has 4 globin polypeptide chains, okay? 2 alphas and 2 betas. So in green and in pink here, we're going to have the globin polypeptide chains, okay? Now, here's the thing. For those of you who don't know, the polypeptide is just a protein. That's it. A polypeptide is just a protein. Okay, I'm not going to get into big explanation, but just for the sake of simplicity, it's a protein. Okay, now there are 4 globin subunits. Okay, so there's an alpha 1, there is an alpha 2, there is a beta 1, and then there is finally a beta 2. Okay, and each one of these guys has a iron-containing heme group on them, which means that a single hemoglobin molecule can bind 1 oxygen, okay, on that iron atom. Okay, that's very important, guys. So we got oxygen here, oxygen bound there, and oxygen bound there. Cool. So you know what we call it when hemoglobin is in this state and in this specific shape where it has bound oxygen? We call it oxyhemoglobin. So that's called oxyhemoglobin, okay? All right. Now let's talk about this one. This is still hemoglobin. It's just the structure of it has changed now, okay? In this specific structure, again, we're still going to have these subunits, the alpha 1, the alpha 2, the beta 1, The beta 2, again, you don't really got to know these too much. Don't worry about them, okay? But in this scenario, now we have other things binding to hemoglobin instead of oxygen, okay? And those other things, guys, are going to be stuff like CO2, right? So you're going to have some CO2 binding there, okay? CO2 binding in this pocket. Other things that can bind are going to be protons. Some protons bind here. Some other protons bind here. There is another thing that binds, and this guy's very special. He binds right here between this beta 1 and this beta 2, pocket between these two guys, and it's going to be called 2,3 BPG. If you remember from the last video, I mentioned this. This is 2,3 bisphosphoglycerate. And you guys remember that I also mentioned the protons and the CO2. If you remember, what I said in the last video was that if you have a high amount of protons, that means you have a low pH. And also if you have a high CO2, the combination of both of these causes the Bohr effect. What was the Bohr effect? The Bohr effect basically describes that hemoglobin now has a lower affinity for oxygen, meaning it doesn't want to bind oxygen as strongly anymore, and therefore it actually lets it go more easily. So the presence of the CO2, the protons, binding to this hemoglobin, changing its shape. You can see that it's completely a different shape when these guys are bound to it, okay? Because it does this, these molecules, they are changing the affinity for the hemoglobin for this oxygen. And in this state, the hemoglobin has a low affinity for that oxygen. Okay? Great. Now, we can say that this region right here, and let's, change this up a bit. This region here is called the CO2 binding site. Okay? Let's just say that's the CO2 binding site. And then we have over here the proton binding site. Okay? Binding site. Okay? Notice how these guys are not binding on the iron atom. Okay? Inside of the heme group. Okay? They're just binding to the globin chains. Okay? The globin polypeptide chains. Now, you guys know that these globin chains are made out of proteins. But proteins are made up of these smaller building blocks called amino acids. Now, really, if you want to get down to the, molecular level of it, the carbon dioxide is actually attaching to specific amino acids groups. For that reason, they say that this hemoglobin, when it's bound to CO2, is called carba-amino, right? So carba-amino hemoglobin. Hemoglobin. Okay? So carba-amino hemoglobin. Because it's carbon dioxide binding to an amino acid. And obviously hemoglobin is hemoglobin. Okay? Some of you might have heard that carbon monoxide can bind to hemoglobin, and that's true. In that scenario, it's not called carboaminohemoglobin or oxyhemoglobin. It's actually called carboxyhemoglobin. Okay, it's called carboxyhemoglobin. When what binds? When carbon monoxide binds. So carbon monoxide, okay, or CO. So that's what that's called. Okay, now, if you remember from the previous video, on top of the protons and the CO2, I said two other things can affect the way that this hemoglobin molecule is functioning, and one of them was high amounts of this 2,3 BPG. This 2,3 BPG, briefly, just very briefly, okay, is going to bind to hemoglobin and make sure that it stays in this exact configuration, okay? So it makes sure that hemoglobin is in this lower affinity state for oxygen, okay? And so if there's more of it available, then more of that reaction is going to start occurring. And the other thing I said was temperature. High temperature can affect For example, the bond that's between the oxygen and the heme group molecule here, okay? Making it a bit weaker. Now, just to very quickly look at the things that can bind hemoglobin, and that's a lot of things, guys, okay? So we know that oxygen can bind. We know that CO2 can bind. We now know that protons can also bind. We know that carbon monoxide can bind. And unfortunately, this guy is irreversibly bound. Okay, so irreversible. Okay, this guy irreversibly binds, meaning that it does not unbind. Okay, and then other things that can bind are actually nitric oxide. Okay, and finally 2,3-BPG, which we just learned about. Okay, so these are all the things that can bind hemoglobin. All right, now briefly a little bit on oxyhemoglobin. You guys remember how we keep talking about the partial pressure of oxygen, right? Well, the partial pressure of oxygen is not actually exerted by the oxygen that's bound to hemoglobin. Okay? You guys remember how oxygen is transported in two ways, right? So one, it is bound to hemoglobin, and that's about 98%. The second way was that it's just dissolved in the plasma. So dissolved in plasma, and that was the other, 2%. Okay? The oxygen that is bound to hemoglobin exerts no partial pressure. No partial pressure. So that means that when I say the partial pressure of the arterial oxygen is about 100 millimeters of mercury, and that the partial pressure of venous oxygen is about 40 millimeters of mercury, I'm not actually referring to the oxygen-bound hemoglobin. I am actually referring to the dissolved oxygen in the plasma. Okay? That dissolved oxygen in the plasma, that little 2%, is dictating the partial pressure of oxygen. Okay? So this is a key thing right here I'm going to write. This oxyhemoglobin does not exert a partial pressure. A partial pressure. And this is very important, guys. This is very important. And I'll tell you why it's important. Because it doesn't actually affect the concentration gradient of oxygen. So you guys know that here's the alveoli and here's the blood, okay? Here's the O2 that is dissolved, okay? And here's hemoglobin. Think about it, guys. If only 2% is dissolved, but 98% is bound to hemoglobin, okay? And I'm telling you that this guy does not exert a pressure, which means normally the concentration gradient looks something like this, about 100 here, and I told you the PVO2 is about 40, so it goes here, okay? But if all of the oxygens that were bound to hemoglobin counted, and they exerted a pressure, their partial pressure would no longer be 40 here. The partial pressure here would be around, I don't know, I'm just making up a number here, but maybe it'll be around, let's say 100, okay? And you see how the partial, there's no longer a gradient? There is no longer a gradient for gas exchange, okay? So the fact that this hemoglobin exerts no partial pressure is a great thing, okay? It maintains diffusion gradient, okay? Diffusion gradient. That's great. Okay. So that's everything on the hemoglobin structure part of it, okay? Now, over here, we're going to talk about the path of a red blood cell that has hemoglobin inside of it, okay? And we're going to talk about how it's taking oxygen and CO2 and transporting them all throughout the body, okay? I find it easier to start with transporting CO2 and then transitioning into oxygen, okay? That's the easiest way I find. Now, just to give you guys such a brief, very brief overview, okay? Here's what's going to happen. At the level of the tissues, and in this case, I have the muscle drawn here, okay? You're going to get oxygen diffusing out of that tissue, going inside of the red blood cell, binding to hemoglobin, okay? But that's actually not the only way it's transported. CO2 is transported in three ways, okay? So one of them is binding to hemoglobin and creating that carbamino hemoglobin that we talked about. The other way, guys, is that it just dissolves in the plasma, okay? And the biggest way, okay, this is the most contributing, way in terms of percentages, is the bicarbonate reaction, okay? And in this scenario, we're actually taking that carbon dioxide, that CO2, okay? And we're going to store it in a quote-unquote storage format called bicarbonate, okay? Bicarbonate, which has a negative charge. So what does that look like? So we're going to go through something like this reaction right here. CO2 plus water, okay, in this reversible reaction turns into carbonic acid, which is H2CO3, and that disassociates into a bicarbonate and protons, okay? This is an extremely important reaction, and you're going to have to remember this, okay? And we'll talk about this more and more throughout, okay? So don't worry, it'll make sense. But this is how CO2 is transported, these three ways. Remember how oxygen was very simple. It only binds to hemoglobin or dissolves in the plasma. CO2 is a bit more complex because it requires these three mechanisms, okay? Awesome. Now, moving on to the oxygen, okay? With the oxygen at the level of the lungs, okay, is going to come inside of the red blood cell, bind to hemoglobin and get transported, or some of it might go into the plasma and dissolve, okay? And the CO2, it'll go and passively diffuse out of the plasma or be offloaded from the hemoglobin or go through the reverse reaction, okay? So from that storage form of bicarbonate, it'll get turned back into CO2 and then diffuse out, okay? And don't worry, if you're not getting it right now, you'll get it completely at the end, I promise you. Okay, so let's get started. So first things first, we got to remember our partial pressures at each level, okay? So what was the partial pressure of CO2 at the level of the tissue? It was greater than 46 millimeters of mercury. 46 millimeters of mercury, greater than that. And then the arterial CO2, the arterial partial pressure of CO2 was about 40 millimeters of mercury, okay? And you guys remember that things like to fall down their concentration gradient, so the gas will go from high all the way to low, okay? And it'll keep doing this until it reaches an equilibrium, okay? Which means that when the blood is actually leaving from the venous side, the partial pressure of the venous CO2 would be around 46, okay? Now, let's get to the bread and bones of it. What does all of this actually look like? Okay, great question. So here you're going to have the CO2, okay? It's coming in, and right here is where it's going to kind of split off into three distinct regions, okay? And I'm going to give different thicknesses for the actual lines to depict their importance. So here, and a little bit thicker here, boom. Let's do it like this. Okay, so we got three lines here, three convergence points, which means what? Which means that CO2 is reacting in different places. So it'll just dissolve in the plasma about 10%. About 10% of the CO2 will just dissolve in the plasma, okay? About 30%, will go and bind to hemoglobin, and we'll show that, okay? We'll show that, not here, but don't worry, we'll show that. And about, the remaining 60%, will go through that special reaction that we talked about, guys, okay? So we're going to take water that is abundantly present inside of this red blood cell at all times. we're going to combine it with CO2, okay? And here's what's going to happen, okay? I'm going to go this way. So I'm going to use the arrow that we're going, actually, I'm not going to say that. Well, you'll see what I mean. You'll see what I mean. So through this reaction, we'll form H2CO3, okay? And then we'll keep going, and we'll form something called bicarbonate and a proton ion, okay? A proton. Boom. This guy right here, he will be pushed out. He will be pushed out as, and I'll talk about this, but let's show it like this bicarbonate here. It'll be pushed out through this special transporter, and instead of it, chloride will come in. Okay, well, why did I just do that? All right, real quick. You'll notice that the direction that we're going is the same color as our resultant that we just formed, okay? So that's depicting the direction we're going, all right? We took the water and the CO2, we put it into its storage form of bicarbonate, and the fate of the bicarbonate was that it goes towards this transporter, it gets pushed outside of the cell into the plasma, and instead of it, a chloride ion comes in. Why do we do this? Why do we do this? This is called the chloride shift. This is called the chloride shift, okay? So when I take a chloride ion and I bring it in instead of that bicarbonate, that's called the chloride shift. Why? Why did I do this? Well, I did this so I can maintain the electronegativity of the cell. Because remember, bicarbonate is a negative ion, and I just pumped it out, okay? If I pump this negative ion out, the inside of the cell becomes more positive, okay? So what do I need to do? In order to maintain the electronegativity of the cell, I need to bring in another negative ion, and that would be chloride, okay? So what's going to happen? I bring in the chloride. To maintain electronegativity of the cell, okay? Electronegativity of the cell. Okay, awesome. Now, another thing. You know this reaction right here? This reaction right over here. It can occur naturally, but why let something occur naturally when you can speed it up? Inside of this red blood cell, there is a special enzyme called carbonic anhydrase. Sometimes you might see it be abbreviated as CA. But the carbonic anhydrase enzyme takes the water and the CO2 and turns it into this carbonic acid very rapidly, okay? Very rapidly. So this is carbonic acid, okay? So that's what this carbonic anhydrase enzyme is doing. It's taking the CO2 in the water and it's turning it into carbonic acid, and the carbonic acid just disassociates into, this should actually be pointing the other way, it disassociates into bicarbonate and a proton. And we talked about what happens to that bicarbonate. It will get pushed out and a chloride ion will be brought in its place. This is all happening at the level of the tissues, at this instant in time. What happens to this proton ion? Some of you might know what from our discussion before, but bear with me here. Let's look at this now, this side, okay? Same red blood cell, but now something is going to change. Also, another thing, what do you notice about the structure, the current structure of it? Is this in an oxy or carboaminohemoglobin state? If you said it's in an oxyhemoglobin state, you're absolutely correct. Because if we go back to the previous slide, this exact configuration was oxyhemoglobin. So right now, this guy should have oxygens bound here, and oxygens bound here. Okay, now, I haven't drawn the CO2's binding yet, and there's a reason. Okay, let's look at this. Let's look at it. So as the CO2 starts coming in, okay, and it starts binding, it starts binding to what? To this hemoglobin, okay? Starts binding to this hemoglobin. And as we keep going through this bicarbonate reaction and we make these protons are going to start binding to this actual hemoglobin. And it's going to change the shape of this hemoglobin in a way that those oxygens that were bound to this heme group right here are going to start to actually disassociate. They're going to start to disassociate because of the binding of the CO2 and the protons. And now look at this. They're going to go down their partial pressure gradient towards the tissues. And of course, the oxygen that's just dissolved in the plasma will do the same thing. That begs the question, what was the partial pressure of oxygen in the level of the tissues? Well, at the level of the tissues, it was less than 40 millimeters of mercury. And at the arterial, right, because remember, we have to talk about what we are entering in with. At the arterial level, the oxygen was 100. And so what's going to happen? It's going to move down its concentration gradient and until this number equilibrates with that number. And so at the venous side, when we leave, the partial pressure of oxygen is going to be 40 millimeters of mercury going to the lungs to get re-oxygenated. Okay, now you guys know exactly how this oxygen is actually being pushed off of this hemoglobin, how it's unloading off of this hemoglobin. It's because there was high amounts of protons being produced from this reaction right here, and there's high amount of CO2 production from the actual tissues. Do you guys remember what it was called when we had that high proton and high CO2? That was called the Bohr effect. The Bohr effect. And the Bohr effect, I told you, is occurring at the level of the tissues. Okay? Now, in addition to that, we said other things like 2,3 BPG can play a role in that. So let's draw that in. 2,3 BPG being bound right here in that little spot. And additionally, the high temperature that's emitting from this actual muscle cell, okay? Because let's just say you're exercising, okay? When you're exercising, your muscle cells are going through a lot of high metabolism, and so there's a lot of thermal energy here. And that is going to actually affect the bond between the oxygen and this heme, the iron, and it's going to make this disassociate even more, okay? So those four factors that I talked about in the last video, they're popping up right here, okay? And they're playing an important role here. But the major ones are going to be the CO2 and the protons that actually bind to hemoglobin, change its shape in a way that oxygen is no longer wanting to bind to hemoglobin because the affinity of hemoglobin for oxygen is lowered. And you can see this because of the way it's changed its shape now. Okay? Awesome. And incidentally, you might be wondering, why can't the 2,3 BPG bind at this stage? Well, it's because these guys are literally closed. The pocket between them is closed. Okay? So, that's what was happening at the level of the tissues. Now, let's actually take this red blood cell here, the same red blood cell that is now deoxygenated, but is in the form of carboaminohemoglobin, and let's go to the level of the actual alveoli. Okay, so let's take this drawing and zoom in on it. Awesome. So as you guys already know, and you are complete experts in, the goal at the level of the alveoli is to what? Get rid of the CO2, okay, so we can breathe it out, and then bring in oxygen into the actual blood, okay? That's the goal here. That's the goal here. So how do we achieve that over here? Well, let's first look at CO2 first, because that's where we left off. What were the partial pressures? So the partial pressure of the venous CO2, that's what I'm arriving with. Logically, just logically thinking about it, because it's coming from the tissues, it should be higher. And it is. It's about 46 millimeters of mercury. The partial pressure of CO2 in the alveoli should be low right now. Okay, so it's 40 millimeters of mercury. There's a pressure gradient here from high to low. Awesome. What's going to happen here? This CO2 is going to keep flowing out until what? Until it equilibrates with this number. And when we leave this alveoli from the arterial side, guess what? The CO2 is going to be around 40, okay? 40 millimeters of mercury. Okay, but what does that look like? What does that look like? All right, I'll tell you what that looks like. So here's our hemoglobin molecule. You guys remember that it had the CO2 bound to it. CO2. It had some protons bound to it as well. Okay? And it also had this special molecule that we said was 2,3 BPG. But it had no oxygens bound to it because we let go of our oxygen at the tissues. We unloaded it. Okay. Now, first things first. First things first. This CO2 that was dissolved in the plasma, okay? Easiest time. This guy will go ahead and diffuse down its partial pressure gradient. This guy was very simple, okay? Very easy to do. Next, the CO2 that was bound to, and you know what? Let's stay consistent with the diagram before, okay? We had the CO2 here, okay, or you know, CO2 here, and we'll just give a line right there, okay? Next thing was going to be the CO2 that was bound to this hemoglobin, okay? That CO2 will come here, okay, and join that line over there. And finally, the biggest one, the biggest contributor was this bicarbonate. But wait a minute. If you guys remember, we pushed this bicarbonate out of the cell and brought in chloride ion. So how are we going to, get it back? Well, luckily, we have another transporter here, okay? This transporter, you know what it does? This guy's a very cool transporter. He is going to, and let's change our colors here to stay consistent. He is going to bring in a bicarbonate ion and push out that chloride ion that we brought in. Now, this bicarbonate that comes in, he is going to combine with the proton that was bound to the hemoglobin. Okay, we're getting somewhere. Now look what's going to happen, guys. Now look at what's going to happen. We're going to drive the reaction this way. We're going to drive the reaction this way, which means that I'm forming what? I'm forming a carbonic acid, okay? Carbonic acid. And then what am I forming? With the help of what enzyme? Well, with the help of the enzyme called the carbonic anhydrase, I'm going to form a water molecule plus a carbon dioxide. Look at that. And this carbon dioxide, and let's make it a bigger size to represent its contribution, is going to come here, and together they're going to contribute fully to this diffusion of CO2 out of the blood. Okay? And you guys remember the name of that special enzyme there was carbonic anhydrase, okay? So here I'll abbreviate it here as CA, carbonic anhydrase. Awesome, guys, awesome. So that's what's happening at the level of the actual alveoli with the CO2. Okay. Now, once this CO2 has gone out, and these protons have gone out, going through that same reaction, okay, what's going to happen is that the hemoglobin molecule is going to start changing its shape in a way that this 2,3 BPG can no longer bind, okay? So, boom, that guy's going to get kicked out. And our hemoglobin is going to start to look like this now. Now that it looks like this, it has a higher affinity for that special molecule we called oxygen. Okay, it has a much higher affinity for oxygen. And look at what's going to happen. If you guys remember the partial pressures of oxygen in the venous side, it was going to be around 40, and in the alveoli it was going to be around 100 millimeters of mercury, which means there's a partial pressure gradient this way. Okay, that's exactly what we want. And this reaction will continue until the partial pressure of the arterial oxygen when we're leaving the blood is about equal to the alveoli. It's about 100. Okay? About. All right, so what is this going to look like? In this reaction, I'll depict it like this. Boom. Here's the oxygen. Okay? That's dissolving in the plasma. And then here is the, and let's show it like this, boom, and boom. Here is the oxygen that will actually bind to those iron-containing heme groups. Okay, so here it is, oxygen here, oxygen here, oxygen here, and oxygen there. Boom, look at that. That's great. That's great. And this is about 98%, and this dissolving is about 2%. Okay? And we talked about how you can increase this in the previous video. Again, if you haven't watched that, go and watch that. So it's very critical to understanding this video. Okay, now that's going to be it for everything you need to know. Now, I always promise to give a little bit of extra information for the people who want it. Because this is a bit of a biochemistry concept, you can stick around if you want, and I'll give you a little bit more extra information. When the 2,3-BPG is bound in this state, okay, it stabilizes the hemoglobin. I told you guys, it stabilizes it and makes sure that it stays in this position. And that position of hemoglobin is actually termed the T state, okay? The T stands for tense, okay? It stands for the tense state. When the 2,3-BPG is no longer there, okay, it cannot stabilize the hemoglobin in this T state. And what happens is the hemoglobin relaxes, okay? These beta 1 and beta 2 chains will close down this pocket here. And now the hemoglobin is in something called the R state, R standing for relaxed, okay? Another cool biochemistry concept is that when the oxygen is binding, at first it has a very, very hard time binding to this hemoglobin molecule. But as it binds, it exhibits a concept called positive cooperativity. Okay? Cooperativity. So what does that mean? Okay. This means that one oxygen binding makes it so the second oxygen has an easier time binding. Okay? Has an easier time binding. And then the second oxygen binding makes it so that the third oxygen has an easier time binding. And the third oxygen binding makes it easier for the fourth oxygen, okay? And you can see that this is continuous. So this is a cooperativity that they express. And the reason for this, okay, one of the main reasons for this is that when oxygen binds to an alpha chain, it causes an approximate 15-degree rotation in the position of the alpha chain with respect to the beta chains. Okay, and that rotation there causes a change between the surface interactions between the alpha and the beta chain, which makes it so that the hemoglobin molecule has a higher affinity for oxygen now. Okay, so again, that's a really cool concept with the positive cooperativity. The first oxygen has a hard time binding. The second oxygen, but when it binds, it makes it easier for the second oxygen to bind. When the second oxygen binds, it makes it even easier for the third oxygen to bind. And when the third oxygen binds, it makes it the easiest for the fourth oxygen to bind, okay? And that's how that works, okay? And we know that this guy will then circulate now all the way to the level of the tissues, and that exact same thing we talked about at the beginning will happen. The CO2 will come down as partial pressure gradient. It'll go through all these reactions. It'll start making protons, which will bind to the hemoglobin, and the CO2 will bind to the hemoglobin, changing its conformation. Okay, once it changes its conformation, it allows for 2,3-BPG to come in and bind, and the oxygens at that same time that's happening will start disassociating because the hemoglobin molecule is changing, the affinity for oxygen is changing, and thus letting go of the oxygen. Okay? All right. Guys, this was a big video. If you understood everything here, and you watched the previous videos and this all makes sense to you, then pat yourself on the back. This is some hard stuff here, okay? That's going to be it for this video. If you like it, please subscribe, please like. These videos take unbelievably a long time to make, so I would appreciate your support. And I will see you in the next video when we start finally talking about the control of breathing. Have a good one, guys.